So one of the reasons I got into this industry is that I love performance. My background is in scientific computing. So it's all about how fast we can make it, how many cores can we throw at the problem, how fast those cores are, and then along came GPUs. The whole point of this was to parallelize programs. We had supercomputers before, we had machines before that can do multiple threads on the same process, but that's got even more important as time has gone on. We've gone through an era where GPUs have been programmed to high heavens. And on this channel, we speak a lot about AI because that's where a lot of the compute is today. However, the pure, raw scientific compute is still one of the most important aspects globally, especially here in the US, but also in Asia and Europe as well. The ability to do simulations like GROMACS, like weather, like nuclear power is more important today than it ever has been. The problem, though, is that the quest for compute has gone down a path of reduced precision. On this channel, you've seen me talk about FP64, FP32, all the way down to 8-bit and even 4-bit and 2-bit precision. That's great for machine learning, but in terms of high-performance computing and scientific compute, you perhaps need a bit more precision than that. Scientific compute isn't fuzzy, it has to be exact. That's why we need things like FP64 to reign supreme. However, FP64 hasn't had the same speed ups as machine learning. And so for a number of people, it's considered to be almost the forgotten child of high performance compute. However, there is one company who is focusing on it today with brand new silicon promising to multiply the throughput and improve the power efficiency of standard scientific compute. You perhaps saw the video on this channel a couple of weeks ago as I'm filming this, about new silicon from NextSilicon, the new Maverick and Maverick 2 processors, introducing a new concept of computing that breaks the mold of standard compute. Benefits here are meant to be multiple, including bring your own code. One of the problems with modern GPUs and ASICs today is that you have to convert your code into their proprietary format. NextSilicon is designed that you can bring that Fortran, that C, and they will help do the optimization both at compile time and at runtime. As part of that, I reached out to the company and we've been working a little bit together. But here at Supercomputing, I'm sat with their CEO, Elad Raz.
Hey.
This 7-year startup, 303, I have to get the extra $3 million of funding. But we've been talking, I mean, I've spent quite a bit of time with these guys already this show about your new Maverick 2. So explain to me why a company in the midst of machine learning being hype is focusing on FP64 and scientific compute.
So first of all, thank you for having me. I do want to address the shirt one because have the Commodore shirt, and one of the things that when you enter the NextSilicon offices, the first thing that you are seeing is my old collection of old computers, Commodores, Atari, the first
Amigas.
8086. We have an Amiga. We don't have the TRS because I couldn't find it. But lots of novel architecture. And the motto is you need to learn from the past, and if you want to invent the future. Okay. Moreover, I'm a software engineer at heart. This is who I am, and it's a very different novel architecture. Per your first question about why not going after the big $26 billion revenues every quarter,
I was going to say,
which is AI and machine learning, is exactly that.
Yeah.
And HPC market is a huge market, $50 billion. That includes everything, also the infrastructure, the cooling facilities, the storage, the interconnect. When you downsize the market into just computing chip, CPUs, GPUs, other accelerators that are tiny a bit there, you get $20 billion market, which is a year, which is huge. And we have those.
We're in a show. There are present. Yeah.
Yeah. So when you look at this market, it's a big market, and it's a market that has a failure because most of the big vendors are chasing the low precision flop, and for them to build the next computing. Okay, I mean those computing chips become way more expensive. So not only per part they need to pay more, but they're getting the same performance at twice the power. It means that they need to spend like 4x more dollar amount to get just the machine that they have today.
Mm-hmm.
For me, as a business owner, that's an opportunity, and you have to generate revenues. So A, it's a big market. B, you can influence it. And the C, and this is what people fail to understand, you can't take every code out there in the supercomputer, hammer it with domain-specific language, hammer it, we vectorize everything, so the NOC will be perfectly with 512-bit going to a scratch pad, like in CUDA it's called shared memory, next to it. I mean, you can't.
I've been through that pain.
You have a graph algorithm, you have lots of different branches. It simply doesn't work. I mean, it's very long instruction set failed. People tried with Itanium back in the days, and you need something else, and here we are. So even with that supercomputing market, you have the tailor-made domain-specific code that people wrote for new GPUs entering from the 2009, and some still buying big CPU clusters, other in the DoD, the defense sector, the Department of Energy, even commercial codes that are CPU only. And think about the amount of effort people had to invest. You talk about the molecular dynamic code GROMACS.
Yep.
You know how long it took until you had the CUDA version of GROMACS?
This goes into a bit because given the buzz that you guys made a couple of weeks ago, people were saying all these codes like GROMACS, WRF, and whatever, because they've been around for a while, everybody knows how the compute is formed, so CUDA and stuff is fine.
Okay.
What do you say to that?
So WRF is the most complicated code out there by far, and as a startup, I can't stand here and say, hey, we accelerate WRF. I mean, it will take us time to get there, but we will get there because all the aspects are here. I mean, we have the chip now. We got them a few months ago. We are seeing the 4x performance per watt over GPUs and CPU now on a narrow set of applications, and we are waiting for the first, at the beginning of 2025, just to reveal those numbers, because we are still tuning them up. 20x over CPU only code. Okay, PageRank, there are codes that are not GPU accelerated.
So how much of that is the HPC market today, do you think, CPU only code?
So
or legacy code, I guess.
I mean, the way I'm not an analyst, I'm a software engineer. But the way that you can think about it is go to the top 500, look at the new system build, with accelerator, without accelerator. Los Alamos, for example, their machine, gray CPU based, is a CPU, not the GPU one. So you have large deployment of CPU only code. We are target both, to be sure. But what we're trying to say, we have a unique value proposition for the CPU only, that user, some users can't find, GPU expert that they get paid like $1 million a year, and you need to invest a few years to port them.
I know a few of those people.
But then what happened by the time you port the application, because you quoted it that you said it's like very easy to write a slow GPU code.
Yeah.
So the porting is the easy part, the tuning is the hard part.
Yeah. That's fair.
But the time you finish the porting, maybe the algorithm changed. I need to
update,
go back. Okay, I need to go back to the sketch code, the drawing board. So the fact that with our accelerator, you can take the code as is, C++, Rust, Fortran. Yes, there are many code in Fortran. WRF is Fortran code.
Yeah.
And just run it, measure A performance, and then we are providing profiling tool and explaining you where the bottleneck in our architecture, because it's different.
Well, okay, so for those people who haven't seen the previous video that I've done on this stuff, how would you describe your architecture and how it's different to everybody else's?
Sure. So we are still waiting about the technology launch to explain exactly how the thing inside the transistor is arranged and how you take a computer program and map it inside the chip. But you need to think about it as the 80-20 rule. This is why we say it's all based on software. Okay, so NextSilicon pivot the problem set from static compilation. Here is a source code I have. I need to vectorize everything. I need to unroll. I need to memory coalesce everything. I need to make sure that the data inside the register, inside the cache size, in the L1 or L3 caches. So we change that into a runtime problem. You take an application, you compile it, you run it, it's run on the host, on the x86. We listen to what important, then we say, okay, this is a computational kernel.
Yep.
We call it a meal, many different reasons. In the in the technology launch, we'll explain why we chose the word meal that John Gustafson, by the way, suggested.
Oh, he's around somewhere too.
He's around, yes. And he has launching his new book.
Yeah, his new book, yeah.
Amazing book. Okay. So we take those blocks and we move them into a world of graphs. So like we as human, we see the world as graph or the problem set as graph, but we need to write serial code inside the programmable language. The compiler take it, transform it back to a graph, and then lower it to instructions, which are serial. The CPU itself, I mean even GPUs, in the processor core is doing the instruction fetch unit, fetch them, and then with the reorder buffer, he convert them back to a graph for out of order execution, which is like dumb. So just keep the graph in, map it inside the data flow. 99% of the people don't understand what data flow is. Okay, there are no instructions. Okay, there is no branch prediction. None of that. I mean, think about FPGA in some sense that you have a lot of mathematical unit or ALUs connected in some kind of topology. Lots of trade secret here in NextSilicon. But it's fit for application that has same program, multiple data, SPMD, which means that you have a single function and a lot of different threads and processes, CUDA stream, warp, whatever the name is, work that happen in parallel. Okay, so that is being etched inside our transistors, and then data can flow in and calculate the things. The important thing is to understand is you want to keep the data and the compute on the chip. But once you move the data set from the static compilation into the runtime domain, it's unlock a new set of runtime optimization. Because suddenly you can listen to the telemetry from the chip, telemetry from the memory, and do things that no other architecture in the world can do.
So you've got a chip like these, and you're getting so much telemetry and feedback back. We've all done profiling on software, right? And it's just you do your runtime and you say, oh yeah, here's the bottleneck and here are the cache misses and whatever. You're doing a lot more dynamic during runtime.
Yes, hence the name intelligence compute architecture.
Right. Okay.
So the point is that those and this is what people don't understand. It's not reconfiguration every clock cycle.
No.
It's not that I reconfigure the next clock. This is
that would be very power inefficient as well.
Just dumb. But you look at massively parallel applications. So you have the same program running on multiple cores, CPU, GPUs, on multiple nodes for hours, days, weeks. This is what we are talking about. All right, GROMAX for instance. So you have a learning. You have like a learning phase, and behind us we have this nice graph.
I was going to say, well, I want you to talk through this just so people understand what it means.
We can do that, right? So you're running the application. You start with the CPU. You get the CPU performance, okay, and then you start offloading. The minute you offload inside this sophisticated chip, 108 billion transistor in 5 nanometer with 8 HBM3E, 6.4 terabyte per second data movement, 192 gigabyte.
You have that off the top of your head. Good.
I have more than that in top of my head. So you immediately start to get in acceleration. And then over.
So we're here.
Yeah, we are here.
Right. Hopefully you can see that.
So we are here. We start offloading. We are here. All right. And this is like the normal optimization that you can do in static one. Okay, take the computational graph, replicate it, optimize it, put the memory in, wait, you start running it. But now you can do more than that. Get hardware telemetry in every second. And I'm not disclosing anything here, so
more details to follow.
Don't take it as face value. But then you take those graphs, optimize them, placing them. Suddenly you understand there is like Amdahl's law. Okay? You optimize something, you find a bottleneck in a different way. Wait, listen to that, place in that, put it in on our data flow, move on. Suddenly you move what we call a slot. You move from one computational phase to another. I did the forward pass, now I'm doing the backward pass. I put it in. And this learning time doesn't really matter in the grand scheme of things.
Yeah.
Because A, we are talking about so many cores for so many hours, so it doesn't really matter, even if the learning time is 10 minutes,
Yep.
which is not.
Yeah.
Okay? And moreover, everything can be cached for the next time that you run the same process.
Yep.
Oh, we remember that, we started from that point. So this is just the initial one. And what is nice about our architecture that doesn't exist in any other architecture is like the Tesla of the world, that you can get a software update and bam, I'm getting 2x performance.
Right.
Processor core is processor core, it's edge, you can't do anything. Micro opcode cache is being used, to handle unlikely instruction in some sense. Okay? No, you can, we just starting, to peel the amount of specialized optimization for this accelerator. So,
So the idea is that something to the right, but you can also get the software updates, and that'll
exactly.
Scale it.
This is
because it's
and this graph is a bit complicated because there are three dimensions here that we try to compress into a single one.
Yep.
You have the learning time, you have the performance, but also what we try to say is about the flexibility.
Right.
Okay, because CPUs can run anything. You get X amount of performance because you have limited amount of performance core, big cores, whatever you want to call it. GPUs, you have way more cores, more parallelism exposed, but you can run a narrow set of application. With us, we are trying to say, hey, you can run anything, like even CPU code and GPU's code, and you can get, I wouldn't say like ASIC-like performance, but that's the best thing that you can get, unless you want to spend $120 million and get like a 5 nanometer chip. And it's just going worse and worse and worse.
So in terms of like CPU, GPU, FPGA, ASIC, that's the standard scale that most people think of.
Yeah, exactly.
Where do we put you?
So I think
Or do we have to
somewhere
do a
between
fifth
FPGA and NextSilicon, between FPGA and optimized FPGA.
Yeah, optimized FPGA.
To an ASIC one in some level, and programmability as easy as you use a CPU. You can just GDB your program, okay, which is nuts.
So I'm being given the hurry up. Can you take us through what chips you've announced?
Sure. So we announced the Maverick 2 in 2 form factor. We have, so we built like a chiplet architecture with 2 chips in 5 nanometer.
Yep.
And 1 chiplet we place on a PCIe 1, which is air cooled.
Yep.
Because you can't get more than like 400 watt is the maximum.
Yep.
So this is like 300 watt. And the 2 of them, we use a form factor similar to AMD MI 200, 250,
so
300.
It's an OEM module.
Yeah, OEM module, which is liquid cool. We are also designing the cooling plate. We have an integration to Penguin servers that they display on their booth and ours here. And like we are really excited about this technology.
So I was looking through the graphics, and I'll put some on the screen because they've got a really good graphics guy. What's Maverick 2 Tango? Is that this version, the 2 die one?
Exactly. Dancing with each other.
So it takes 2 to tango. Is that what it is?
More than that. Look at the.
It says a die to die for. One of the things that interests me, and this is any company can do this. These guys have a lot of in jokes. If you look into their materials, and it just shows that there's a level of dedication and passion that you don't have to be rigid on this stuff.
Yeah.
I mean, if you have a flexible architecture, flexible software runtime for flexible code. So I know we've mentioned high performance computing. Where does inevitably the question goes to machine learning? So what can we talk about machine learning when it comes to these? Because no doubt when people get these, they're going to run machine learning code on it.
Absolutely. All right. So a little bit of physics. If you put a multiplier of 64-bit, I mean, multiplier it's hard in hardware because you're doing like a multiplication on the first grade. There are some optimization that call boof algorithm, but essentially you move the bits in and then you need to summarize everything. And you can have like a data tree or marker that lower the latency of the multiplier, but it's big. 64 multiplier hardware design is 4 times more expensive than 32-bit, 4 times more expensive than FP16 onwards. Okay, And the normalization factor is also big, like 16 is way easier. So you can put petaflop of FP16, 2 petaflop or even a bit more of FP8. Wait, you put 60 teraflop of FP64, okay, and 40 in the new one. Not nearly enough.
Right.
So yeah, you can run machine learning code here and PyTorch and take the lead dynamo and the lib810 and just run it. You won't get amazing performance. But what I do want to mention, and this is like a business decision, and then we'll go to technology one, okay? So business-wise, if you want to sell a supercomputing of AI machine learning, it needs to perform at scale. The type of customer that you are talking to, they don't care about the underlying hardware. You and I can geek out all day long about the technology.
They care about tokens per watt, tokens per dollar.
I think that the only benchmark is performance per power per dollar. Okay, token per second is how you scale the machine. That's my humble opinion. Okay, but you need to prove your architecture at scale, at deployment, with all the thousands of Hugging Phases model, and we've seen Lisa Su on the stage, really proud on the fact that they can run so many models out of the box, and kudos for AMD on doing that. Okay, so they tend to be, what I'm trying to say, they tend to be late adopters. Prove yourself in the HPC market, get a real business, get tangible revenues in, build a business rather than a startup. Prove yourself in large-scale deployment. Now it's easier to sell to the, it's always hard, but easier to sell to the private sector because the big supercomputers are based on NextSilicon architecture.
If you got the buy-in from the government,
yes,
it's a lot easier to...
But the other things that I want to say is future-proofing. No one knows how neural network algorithm will change. I mean, you have Triton that you can write your own ML ops, and users playing with that, and NVIDIA has a nice general purpose like kind of topology that user experience. And we are seeing how neural network evolve from CNN convolution that you need to run convolution and max pool and ReLU. And then you got transformers on the other edge that you need to run exponent and inverse square root and hyperbolic tangents. You know, shit. If I don't have it in the hardware, I'm dead. So you could edge that say, let's build a dedicated chip that run only Llama. What will happen in 2 years if algorithms change? You're out of business, right?
Or you're stuck on an old algorithm that isn't performant.
Yeah, and someone told me yesterday, like HPC has the most complicated code out there. So it's like climbing a 10-foot wall. You've done it. Now doing the AI one is just a 10-foot wall. And what's nice about our technology, if we can accelerate, you know, those quasi stencil or math, you know, not just linear algebra for the HPC. Future MLOps are, you know, based on physics and math. They will use those primitives. We are poised to lead that market as well.
Okay. That you're so predicting big things in the future, but get the hard stuff done first.
Yes.
The HPC stuff.
Exactly.
These guys are looking to produce some benchmark numbers in Q1, I believe.
Correct.
Over a wide set of software. So we'll get those in, and we'll make sure that they're competitive and put them against the competition. But good luck.
Thank you very much for having me. I enjoyed this interview.
And we'll see you in Q1 for sure. To me.
Thank you very much.
Awesome. Thanks, Elad. Cheers.